All right, so whenever we're dealing with stairs, one of the first things that I do is draw a quadrant, right? Quadrants are a fantastic tool that we use entirely for stairs, for rafters. We use them all the time. Anytime we're actually trying to calculate sides of proportional triangles, the quadrant is our best friend. So the first thing I like to do is let's go ahead and identify the triangles that we're dealing with here. One triangle is always your finished or your rough opening triangle. And the two sides that we deal with here is the rough opening itself. And then we also have, here it says drop to the line of flight, but we call this Q. Okay, so we call that Q. Keeping in mind, what is Q made up of? It's made up of the vertical distance. This is a vertical component, a rise component from the line of flight all the way to the top of the finished floor. So we have a horizontal component, a run component, which is our finished opening. We have the rise component, which is Q, which is comprised of the headroom required and the floor assembly. And what are we comparing that with? We are going to compare that with its proportional triangle, which is our step, right? We have the rise and the run of our step. So our little triangle down here, which is the rise and run of our stair, is directly proportional to the large one. So we draw out a quadrant. So let's go ahead and we're going to label this. So making sure that we're always comparing apples to apples. So if on this side, I'm going to put my two labels, my rise and run labels on here. So I have a rise and then I have a run. So of course, here's my rise component and here's my run component of my small triangle, which is my step. And then, of course, I want to compare apples to apples. If I put rise on top, I'm comparing that to the rise component of my larger triangle, which of course is Q. That's the rise component, rise to rise, run to run. So sometimes you'll hear the term, the rise is to Q as the run is to our stairwell opening. Okay, so making sure that we have a vertical component, a rise component, and run components that are matching. Now that we have it labeled, we can go ahead and just start working through the math, and we'll fill in our labels as we go. So let's get our friend, the calculator, going here. Number of risers. Let's go ahead and let's identify some of the things we need in here. The total rise for the proposed stairs is 3090. So that's our total rise, and we're looking for a unit rise of 175. So we call this our desired rise. So we have, let's calculate the number of risers, the unit rise, and then we'll continue on. So we calculate the number of risers by taking our total rise, the distance, and of course that will be from our bottom of our floor all the way to the top of our finished floor. That is our total rise. We'll take this and we need to break this up into how many risers. How many of these risers do we have? So we'll take the 3090, we'll divide it by the desired rise, which is our target. This is what we're aiming for. In this case, we have 175. We end up with 17.657 risers. Of course, we have to deal with whole numbers of risers only, so we use our rounding rule. If it's 0.5 or greater, we round up. If it's anything less than 0.5, we round down. So in this particular case, we have 17.657. We will round up to 18 risers. Because we have 18 risers, minus 1, and that's the number of our treads. And it doesn't have our tread number here, so I'm going to go 17 treads at, and then I'll put the tread in here, okay? So always one less tread than riser. So now let's calculate the actual true rise per step by going back to our total rise of 3090. And we'll divide this now by the whole number of risers that we've rounded to, which is 18, which gives us a true rise per step for these stairs of 171 point, we'll go to 0.7, we'll round to the nearest first decimal place, 171.7. Okay, perfect. Now, in order to calculate the unit run, in this particular case, we're using the 430 guide. So this is our rule. If we're given a rule, we use it. And the rule 430 is the unit rise and the unit run together equal 430. So we can simply take 430, subtract our unit rise, our true rise per step of 171.1, and then we get our unit of run. In this case, it is 258.9.
You did 171.1 instead of 7.
Yes, I just caught that. 430 minus 171.7. That's a little better. 258.3. Okay, so now we have our unit rise and unit run. Since we have those, let's apply those to our labels up here. So our unit rise is 171.7, and our unit run is 258.3. Excellent. So our drop to our line of flight, or Q, is of course going to be a calculation of our headroom required plus our total floor. So let's go ahead, and I'm just going to list my floor assembly here. Let's get all the parts of our floor assembly. We'll get them highlighted. So what do we have here? We have a headroom required, of course, is 2055. So we'll come back to that. And we already have a total floor thickness. Oh, that's just way too easy. We don't have to actually add all these things together. So a total floor thickness of 3090. We'll add that to our desired headroom clearance of 2055. 2055 plus our 390 gives us a value for Q of 2445. Okay, once we have 3 parts of our quadrant populated, we can cross multiply and divide and find our missing quadrant. So in this case, of course, we cross multiply diagonally and then divide. So 2445, we'll multiply that by our unit run of 258.3, and then we'll divide that by our unit rise of 171.7, gives us a stairwell opening to start of 3678.2. Now, what do we have to typically do when we're dealing with wood stairs?
Hey, Bob.
Yes.
Sorry to cut you off, but what did you add to get that height again from the top of the tread to you just added?
For this, the two numbers that I add, you use the floor assembly. That is the thickness of our floor here, which in this case is 390. And then we're using the headroom clearance that is desired. So from our line of flight to the underside of our header.
Oh, you said
yeah, is our headroom of 2055.
Right. Okay.
Both of those together gives us the total vertical distance of Q.
Right.
So then we cross multiply divide, we end up with our stairwell opening. And now, of course, since now the typical rule is we add on for finishes, of course. We generally add 75 millimeters for finishes, but in this case here, it's actually giving us our numbers already. It says here, the attachment at the head, top of the stairs requires 53 millimeters of allowance, and 27 millimeters is required to apply a finish material to the header. So all of these together gives us an additional 80 millimeters. So we're going to add these 80 millimeters for clearances and finishes. So plus 80 ends up giving us a total rough opening of 3758. And then, of course, our finished opening is minusing off these clearances of 80, which is our 3678, the first number we had before we added these finishes. And then, of course, our drop to the line of flight, which is Q, is 2445. So as we go forward, some of the terminology is going to change to something more consistent for you. And the finishes typically are not given, and the assumption is always add 75 mils. Okay, so when we're dealing with wood floors or wood framing, whatever the stairwell opening is, we calculate, we always add 75 mils for finishes, unless of course it's concrete, and we add nothing.
I got I did the process completely right, but I rounded to 172 and 258 because it still went to 430, but then my numbers at the end were a little different. So you would just go to 1 decimal place instead.
Yeah, I mean, you could round up just to the nearest whole number of millimeters. Your numbers are going to be close enough that it's not going to make a difference on.
Yeah, it was really close. Yeah, perfect.